It's a pleasure to be here, and I would like to thank the organizers for that. Also, this will be the last talk of the day. So I'll talk about the project that started a long time ago. Actually, most of the progress, I think, was done in 2007, and then the project got kind of stuck, and it took off during the Corona pandemic when, well, the four authors learned that they could communicate also via Zoom. And so finally, we managed to, well, finish a preprint at least a few weeks ago. So the motivation is understanding in a more systematic way some reduction procedures for Courant algebroids that appeared in several papers around 2005 and 6, notably the one by Bursztyn-Cavalcanti-Gualtieri. But I'll say a bit more now. So I'm also happy that I can well, use some of the material that the previous speakers explained today. So this slide was already explained by Thomas early this morning. And so this is about symplectic geometry, and I have this slide here because what I will do will be a graded geometric version of this, and I will tell you soon why. Okay, coisotropic reduction, so we have a symplectic manifold. So inside symplectic manifold, there are some submanifolds that are particularly nice, the coisotropic ones, and they come with a foliation, so as Thomas Strobel told us today, actually involutive distribution, involutive distributions or foliations is the same. So when we're lucky, the leaf space is smooth, and when it is smooth, it inherits a symplectic structure. So that's the n underline that I have up there. And there is an algebraic way to explain this because, well, instead of the symplectic form, you can use the Poisson bracket on the smooth functions on the manifold and express everything in terms of that. So the quotient, I don't know where the laser is. Well, maybe there is no laser. So so to get the functions in the reduced space, you take the vanishing ideal of the submanifold n, it's Poisson normalizer, and then you take the quotient. So this is the Poisson algebra. So a special case of this is given, well, as Thomas said today, by Martin-Weinstein reduction, also known as Hamiltonian reduction. So in that case, we start with a symplectic manifold with a group action, preserving the symplectic form. If we are lucky, it has a moment map, whatever it is exactly. And the preimage of 0 under the moment map is always coisotropic, if it is smooth, and the quotient, then it's always symplectic. And this is a special case of the coisotropic reduction that I have up there. Okay, so the point of the talk is to, well, carry out this in the world of degree 2 graded manifolds instead of ordinary manifolds. So Madeleine in the previous talk called them 2 manifolds, 2 in brackets. And the motivation is that this allows us to get some, well, statements about ordinary geometry, namely about Courant algebroids. And well, I wanted to say something about Courant algebroids at the beginning because maybe not everyone is familiar. So that's an example. If you have a manifold, the tangent plus the cotangent bundled together form a Courant algebroid, and the most important part of the structure is the bracket on the sections, which is called Courant bracket, and it's not skew symmetric, so it's not a Lie bracket. And so Courant algebroids are important also because they are the place where several kinds of geometries live, sometimes called generalized geometries. For instance, Dirac geometry. So Dirac structures are sub-objects in a certain sense of Courant algebroids. And Hitchin's generalized complex structures can also be viewed as some kind of objects that live on a Courant algebroid. Okay, so that's where I want to go. So let's start. So at the beginning, I will say a few things about degree 2 manifolds. And I think they will complement mainly, they will complement in part what Madeleine said. There will be a couple of repetitions, but I will be a bit fast about it. So this is a tool that we use in the paper, and this complements what Madeleine said. And well, I think it's interesting enough that I can spend a slide on this. So let's take a degree 2 manifold. So we have the body, so M, and a sheaf of graded commutative algebras that I call CM. And okay, so what do we know? So if I take I'll point to here, I don't know where to look. So the degree 1 functions are a module over the degree 0 functions. which are just functions in the body, right? So they're a module, and further this module is, well, locally finitely generated and locally free, so those are sections of a vector bundle. I can call this vector bundle E1 star if I want. The same holds for degree 2 functions. And furthermore, there is a relation between these two vector bundles because the product of if I take a pair of degree 1 functions and I multiply them, I get a degree 2 function, obviously. So I have an injective map that translates into an injective vector bundle morphism that I call I there. And it turns out that this data characterize, well, up to isomorphism, the degree 2 manifold. So there's a bijection up to isomorphism, actually an equivalence of categories between degree 2 manifolds, and triples consisting of vector bundles E1 and E tilde, defined as up there, and, well, a map, right, this phi E is that map down there, this surjective map. So what I wrote here is just the dualization of what I wrote up there. Okay, and at the end I wrote how, given such a triple, you can recover the sheaf of functions, the graded commutative algebras on the manifold.
What is T?
So T, let's see. So T is an element of the first space of sections there. So, sorry, I should say it in a simpler way. So T is a degree 1 function, so say a section of E1 star. And
So you do that for all T?
Sorry. Probably I should do this, right? So the meaning of this is that, if I don't quotient out, I have redundancy. I have certain, I have products of degree 1 functions, but I want to view them as degree 2 functions. That's why I have to divide by this.
So you do it for all T?
Well, I think I do this. I do it for all T's that lie in here, and that bracket means the homogeneous ideal generated by those. So I think this is precise. Okay, so okay, now so I will need to use submanifolds of degree 2 graded manifolds. And one way to, specify submanifold is by specifying its morally its vanishing ideal. So this slide is about that. And so not every ideal in this sheaf of graded commutative algebras is nice. So we call the nice one regular. That's the definition. So the main feature is that, like locally, if we choose coordinates on the degree 2 graded manifold, this ideal is generated as an ideal by a subset of these coordinates. And okay, so instead of talking about submanifolds, I will talk about ideals to do all the constructions. And as usual, you recover functions on a submanifold by taking the quotient between all the functions and the vanishing ideal. Well, and that iota inverses because we're working with sheaves, so I have to pull back to the body of N, so the submanifold N. Okay, so this still preparation. And actually, I will work in the world of symplectic degree 2 manifolds. And so what should that mean? There are various ways to say it. This is the simplest, for me at least. So on this degree 2 manifold, we take a degree 2 Poisson bracket on the space of functions. So these curly brackets, is something where you plug in a pair of elements of CM, of functions, and you get another function of degree equal to the sum of the degrees minus 2. It was graded skew-symmetric and graded Jacobi. And, and it's a by derivation of the product in every entry. Okay, so that would give us a degree 2 Poisson manifold. So symplectic means that the bracket is non-degenerate in some sense. One can write it down in coordinates, for instance. And this is a way to say it. So using the bracket at every point of the body, of the degree 0 part of the graded manifold, we get a linear map between these two graded vector spaces, the cotangent space at x and the tangent space at x. And when that map defines an isomorphism, well, we say that the Poisson bracket is non-degenerate, and we talk about symplectic graded manifold. So I, the notation is as at the beginning, so I is basically the vanishing ideal, just at the level of Stokes here. Okay, and so let me review, but maybe I should do this a bit faster, something that Madeleine also talked about, namely the bijection after isomorphism between symplectic degree 2 manifolds and pseudo-Euclidean vector bundles. So Madeleine called them metric vector bundles, so that funny bracket up there is just a symmetric non-degenerate bilinear form on every fiber of this vector bundle E. Okay, in one direction is easy. If you have the graded manifold, you can take the vector bundle that well, gives you the degree 1 functions, and the Poisson bracket has degree -2, right? So if you plug in a pair of degree -1, no. If you plug in a pair of degree 1 functions, the result is a degree 0 function, so that gives a pairing. And well, going the other way around involves this T algebroid. So let me just remark something. So degree 2 manifolds in the description characterization that I gave earlier correspond to a pair of vector bundles together with some map. And here somehow there is just one vector bundle. That's because the second one comes for free. So if you start from the pseudo-Euclidean vector bundle, well, you take E star as the vector bundle whose sections are degree 1 functions. And for degree 2 functions, you take a vector bundle that is actually Lie algebroid that is canonically associated to the pseudo-Euclidean vector bundle, namely it's a tier Lie algebroid. And so its sections are covariant differential operators that preserve the metric. And well, and since we have this short exact sequence, like the first map here is an injection, so that gives you the map in this characterization of degree 2 manifolds I gave at the beginning. Okay, so this is due to Roytenberg, and I learned today also to Pavel Shevera. And so I also heard people saying that Weintraub had, knew about this, but I'm not sure. Okay, so what's the idea? So I'm interested in Courant algebroids, and Courant algebroids are in particular pseudo-Euclidean vector bundles. So let's do one thing at a time, and so I can use the fact that pseudo-Euclidean vector bundles corresponds to something quite intuitive in the world of graded manifolds to work in the world of graded manifolds, doing symplectic reduction or something like that, and then go back to the ordinary world. And so that's what's happening here. Yeah.
Should we think of that as a sort of Weinstein-Darboux theorem? Or what was the role of the closure of the symplectic form in this?
You're asking why the symplectic form, where you're asking what is used So let me think 1 second, sorry. So that comes in the second, like in the direction from the one that I wrote at the bottom of the slide, from pseudo-Euclidean vector bundle to symplectic degree 2 manifolds. Well, you get, so I didn't say how you construct the Poisson bracket. So, well, for a pair of degree 1 functions, it's written there. And then for when a degree 2 function is involved, you use the fact that degree 2 functions are operators that act. And so the bracket, for example, of 2 operators is just the intercommutator, the graded commutator, and that satisfies the Jacobi identity. So it comes out for free. Yeah. Okay, so let's try to understand coisotropic reduction in the graded setting, and then I'll translate to the ordinary, to the world of ordinary manifolds. Okay, so what is a coisotropic submanifold? Well, it's a submanifold of this degree 2 graded manifold. And so that the ideal that defines it is closed with respect to the Poisson bracket. So this is just as in ordinary geometry. Okay. So now I would like to translate the fact that the submanifold is coisotropic to ordinary geometry, and that means I want to express it in terms of this pseudo-Euclidean vector bundle, the one I have in the upper right corner. And it turns out that the coisotropic submanifold corresponds to a bunch of data. So it's a quadruple, and I will try to make a little drawing to, well, make this a bit more understandable. Well, not a drawing. I'll just write the same thing in a slightly nicer way, maybe. So we have the following. So we have a subbundle of my pseudo-Euclidean vector bundle. So N is a submanifold of M, and K is an isotropic, actually, subbundle in here. And then we have two additional pieces of data that I will write down here. So on N, I have a foliation. And furthermore, there is a flag metric connection around. So this is an F connection, not on the isotropic subbundle K, but on some other vector bundle constructed out of it, namely K perpendicular divided by K. Well, perpendicular, of course, is with respect to the pairing. Okay, so these are the data you get if you work a bit and translate. Okay, so just to give you an idea of how the correspondence goes, this is one direction. So if you have such a quadruple, well, you want to specify, well, this ideal. So it's a homogeneous ideal, so it's enough to do it in degrees 0, 1, and 2. In degree 0, well, you just take the vanishing ideal of the submanifold N. In degree 1, you take sections of the vector bundle E, which over N restricts to K. That's what this symbol means, lambda EK. And in degree 2, we know that, we know that degree 2 functions are sections of the T algebroid. So this covariant differential operators on E satisfying, preserving the metric. So I have to specify a subset of those, and I take those which somehow are compatible with the foliation and with K. So the symbol of the covariant differential operator restricted to N lies in F in the foliation, and the covariant differential operator preserves the sections that restrict to K and plus one more property. Okay. So a special case of this has been known, was known much earlier, for example, by Pavel Shevera, and namely the case where the coisotropic submanifold is actually Lagrangian. So Lagrangian, one way to say Lagrangian is coisotropic, and the total dimension is half of the total dimension of the symplectic graded manifold. So if you specialize this quadruple thing to Lagrangian submanifolds, all you're left is a Lagrangian subbundle. So then, the connection disappears because K perp divided by K is just, has rank 0. So some data disappear. Okay. And okay. So now that we know what a coisotropic submanifold is in this graded world, we can try to see when can you do reduction and get a degree 2 symplectic manifold. And as in the ordinary world, we have to worry about smoothness. So this proposition is about when you get a smooth, when you get an honest degree 2 symplectic manifold expressed in terms of the ordinary data. So let me go back 1 second, sorry. So expressed in terms of this quadruple there. So the conditions are that the foliation on N has to be, what's it called? Well, the quotient has to be a smooth manifold, and also the connection, this connection here, which is flat, must have no holonomy. So if you take like a loop in a leaf and you follow and you do parallel transport along the connection, when you come back, you want to get the identity. So you don't want to divide the fiber by something funny. And okay,
What
so
does reduced mean?
sorry.
What do you mean by reduced?
Okay, so what I wrote in the line below. So the statement is there exists a symplectic degree 2 manifold denoted and underlined with the property that so its sheaf of graded commutative its functions, basically, the sheaf of functions, is isomorphic to the thing on the right there. So you take the vanishing ideal of the coisotropic submanifold, you take its normalizer, you divide, you pull back, and so that should be isomorphic to the functions. Both carries Poisson structures, Poisson brackets, and you want the isomorphism to preserve the Poisson brackets.
Curly n is supposed to be n mod f? Like, I mean, on the body of it?
So curly n, no, I think not. So
I'm trying to understand this before the p that you're doing.
yeah, so curly n is this coisotropic submanifold of curly n. So both have a body. The body of this is denoted by straight m, and the body of this is denoted by straight n. So a piece of notation I haven't explained there is what this p is. So p goes from the body of n to its leaf space.
But maybe we can talk later, but I was confused because you push forward something down to n mod f, whereas Cn is supposed to live on n.
Cm lives on n, yes.
It's supposed to be alpha stars or low sum?
I think the star is okay. So the iota inverse pulls everything back to n, and then
what's the body of n underline?
it's this one.
Okay, yeah, that's not I asked at the beginning, but you just.
Oh, okay. Sorry.
Okay.
It's that one, the leaf space. So, okay, so what is this? Well, so we have a quotient, a reduced, well, by this quotient procedure, we got a symplectic degree 2 manifold. So we know that it must correspond to some pseudo-Euclidean vector bundle. Which one is it? It's this one here. So it's the one on the right. So basically, to get it, you take k divided by k, which is a vector bundle over n. And then on the base, you divide by the foliation. And for the total space of the vector bundle, you divide, well, you also divide by a foliation because you have a flat connection. And that gives you, well, leaves. So you divide by that. Okay, maybe I will not make a drawing for this. Okay. So now I will bring, well, a little bit of extra data in the picture because, well, I don't only want to talk about pseudo-Euclidean vector bundles, but actually about Courant algebroids. Okay, well, here this is the abstract definition in case you haven't seen it. So we have a pseudo-Euclidean vector bundle with a couple of more data, notably this Courant bracket. And so on the graded side, so I want not just a symplectic degree 2 manifold, but, well, what we call here Courant function, this theta in the middle. So that's a degree 3 function, which Poisson commutes with itself, a non-trivial condition. So if you take the Hamiltonian vector field of this function, you lose 2 degrees because the Poisson bracket has degree minus 2. So you get a degree 1 vector field which, well, commutes with itself. In other words, M becomes a differential graded manifold. So this theta, if you don't like to work, with the function theta, you can just think M is a differential graded manifold where the homological vector field is Hamiltonian. Okay, and well, it's theorem by Roytenberg and Chevera says that, well, so we get a bijection even after this upgrade. So on one hand, Courant algebroids, on the other, symplectic degree 2 manifolds with such a function. And I will not really say how this goes. Okay, so what about, so does this survive reduction? Well, we have to put some extra conditions because so now we have this extra data, this degree 3 function. If I take a coisotropic submanifold in the graded world, I cannot expect that this function induces something on the quotient for free. And so a sufficient condition for the degree 3 function to induce a function on the quotient is that it lies in the normalizer of the vanishing ideal of the coisotropic submanifold. Or in other words, that theta, for some bracket, the vanishing ideal, preserves the vanishing ideal. And yet another way to say it is the homological vector field, which is just the Hamiltonian vector field of theta, is tangent to the coisotropic. So we have again a Dirichlet manifold. And okay, if you translate into the ordinary, like into the classical data, you get a bunch of conditions on the anchor, so this map from the Courant algebroid to Tm, and on the Courant bracket. So the most important maybe is the last one. So sections of my Courant algebroid which restricts to section of k perp, and when we go to the quotient dividing by k are flat with respect to the connection, those are supposed to be involutive with respect to the Courant bracket. Okay, again, in example, special case, when n is Lagrangian, so we get, Lagrangian subbundles with these extra properties, they behave well with respect to the Courant algebroid structure. These things are sometimes called Dirac structures supported on a submanifold N. And so putting everything together, we get that, if you have a Courant algebroid, pass to the corresponding symplectic graded manifold, take Courant algebroid, take a coisotropic submanifold. If the regularity conditions in A are satisfied and the conditions in B, which guarantee that this Courant function descends, then you get as a quotient, a degree 2 symplectic manifold with Courant function, and we know that corresponds to Courant algebroid. So of course, as a vector bundle is just the old thing. K perp divided by K, and then divided by this foliation given by the flat connection. Okay, and before I switch to the second part of the talk, let me make one little comment about one of the extra geometric structures you can put in Courant algebroids. For instance, generalized complex structures. So they are endomorphisms of E of this Courant algebroid, the square to -1, whose 9-hours tensor with respect to the Courant bracket vanishes. And Grabowski realized that they can be interpreted as functions on the degree 2 symplectic manifold associated with the Courant algebroid. There is a minus sign missing there. And and then, so if you want the generalized complex structure to descend to the quotient, you have to ask something. The condition is just was written here. Then the morphism have to preserve certain sections that restrict to K perp, et cetera, et cetera. If that happens, then it descends. Yeah?
So I just want to make a remark. The remark in the middle that only holds in the exact case.
So you're saying Grabowski's characterization only holds in the exact case?
I think he even said that.
Okay.
In principle, you can have theta to be 0. That's an admissible Courant function. And then every quadratic J is satisfied.
Okay, that's, but okay. Yeah, but theta equal to 0 is also okay, no?
Yes. But that would mean that you can take any J, and that's not true.
Right. Okay. So you're saying that I shouldn't have written equivalent there in general.
In the exact case.
Yeah. Okay. Okay. Thank you.
By quadratic, do you mean a function of degree 2?
No. By quadratic, I mean something that lies in C1. So this is a curly M times C1.
It's a product of two functions.
Yeah, because this is isomorphic to or something like this. So skew-symmetric endomorphisms of E live there. Yeah. Okay. So thank you for the comment. So So this condition, this characterization of the statement actually holds for any quadratic function. So it's just, so the usefulness of knowing that generalized complex structures, well, satisfies, at least in some cases, an equation like that one is just to say, well, if that equation is satisfied, on M, then it also satisfies on the quotient. Like passing to the quotient, doesn't do anything funny to the Poisson brackets. So whatever relation curly J satisfies before going to the quotient, it will satisfy the same relation on the quotient. Okay. So I will not say anything more about generalized complex structures, but well, maybe I have time. So can you remind me how much time I still have? 25 minutes? Okay, thanks. So I'll take 1 minute to make a very short recap before I switch to something slightly different. So this is just a very quick summary. So this is the graded geometric part side. So let's take a symplectic degree 2 manifold. Okay, inside here I looked, this is supposed to be an N, at the coisotropic submanifold. And well, if you're lucky, well, you can take a quotient of it, which is again, which I call an underline, and which is again a symplectic degree 2 manifold. Okay. So and on the classical side, this corresponds to a pseudo Euclidean vector bundle. The coisotropic submanifold corresponds to this funny quadrupole. Well, whatever, I'll write it like this. F. And well, and the quotient is this vector bundle over over the leaf space N mod F. Okay, and then I brought into the picture Courant algebroids, so to say. So here I added this Courant function, which just means that, well, basically M now is a symplectic DG manifold. Then when the homological vector field is tangent to the coisotropic, well, on the quotient we also get a DG structure. And okay, on the classical side, adding the theta just means that I put Courant algebroid here and here. So this is a quick summary of what I did so far. Now I'll, specialize in a way. And okay. So now I will pass to the Hamiltonian part of the story. Okay, so I don't have it here. Well, so what do we have? What do we start with? A degree 2 symplectic manifold, but we also need an object that acts on it. Well, let's work infinitesimally, so no groups or things like that. But we look at some kind of objects that act infinitesimally. So let's take a graded Lie algebra, and let's take it concentrated in degrees -2, -1, 0. So the coordinates of M are in degrees 0, 1, 2. Here we take those are the coordinates. And well, hopefully this will make sense in a second. And okay, to do things properly, I should say what an infinitesimal action is. Well, that should just be a morphism of graded Lie algebras from G tilde into the vector fields, and then say, the action has a moment map if blah, blah, blah. So to save time, I'll do it the other way around. I'll say immediately what the moment map is. Some people might call it co-moment map. No, sorry. This is really moment map. So moment map is a morphism of graded manifolds from M to G tilde star, well, with a degree shift. And so that is the most important part of the data is what the pullback of functions is, so to say. So that's a map from G tilde to the functions on M with some degree shift. And I want that to preserve brackets. So which brackets? Well, on G tilde is a graded Lie algebra, so of course I have a bracket there. And on the functions on M, I have the Poisson bracket. well, and as in usual symplectic geometry, out of a moment map, you get an infinitesimal action just by taking, that's the last line, just by taking the Hamiltonian vector fields of the components of the moment map. And, okay, okay, just 1 second, okay. So let's look at the co-moment map, the thing in the middle. So if I take homogeneous elements of G tilde and I look at their image, I will get functions on M which have degrees 0, 1, and 2. So the degrees that generate the algebra functions. And similarly for the infinitesimal action, the images will be vector fields of degrees -2, -1, 0, and those are exactly the degrees that generate the space of all vector fields, well, as a module. So those are the vector fields in degrees -2, -1, 0 are the only vector fields which have a chance not to vanish on the body. And so this way we still have a chance of having a free action or almost free action.
Is there an example we should have in mind for this G tilde?
Say it again?
Is there an example we should have in mind for this G tilde?
Yes, there are examples in the literature. I will get to it a bit at the end, but not very explicitly. So for instance, you can construct such a thing if you take a Lie algebra G, so the same G as there, and if you take a module for it, a module. Just with these two data, you play a bit around with it, you can construct such a thing. So this is in the old work of Bursztyn-Cavalcanti-Gualtieri, actually. So this construction, this thing that I'm telling you, is in the work by Bursztyn-Cavalcanti-Gualtieri from 2007. It's just that I didn't phrase it in these terms. Okay, so what about reduction? Well, okay, one can check that if 0 is a regular value of the moment map, well, and this makes sense also in the graded setting, and then one can associate to it a submanifold of M, well, which I suggestively denoted by inverse image of 0 under the moment map. So its vanishing ideal is given by pulling back the vanishing ideal of the origin in G tilde star 2. So that's coisotropic. One can check quite easily. And at this point, I can use the coisotropic reduction that I talked about before the summary to conclude that under regularity conditions, one gets a reduced degree 2 symplectic manifold. So I don't need to do reduction again. This is just a special case of the previous one. Okay. Now, so what about adding the extra data, namely the Courant function? So suppose that M is not just symplectic, but has a Courant function. Well, then it makes sense to upgrade G tilde, which was so the object that acts. So that should not be just a graded Lie algebra, but a differential graded Lie algebra. So I'll try to convince you in a second. Well, actually, in the next bullet point. And then the moment, or the co-moment map, should be then not just a morphism of graded Lie algebras, but of DGLAs. Okay, so I explained this very badly. So look at the last item there. So if M is just symplectic, on the functions we have a Poisson bracket. Now, if I have this degree 3 function, or if you want this homological vector field, I get a differential, right? Because the vector field acts on functions in a way compatible with the Poisson bracket. And so I have a DGLA. And once I have a DGLA on the right side, that the functions on M, well, it makes sense to ask that you have a DGLA on the left side, and that the map preserve the differential too, not just the bracket. So that's what's happening here. And okay, so let's assume this. These are all assumptions. Well, then on the quotient symplectic degree 2 manifold, you get for free a Courant function. So the Courant function descends automatically. So that's the consequence of the fact that the co-moment map preserves differentials. So I wrote it in formula here. It's hard to read, I guess, but it follows immediately from the third bullet point. Okay, so what comes next? Okay, So all of this is in graded geometric terms. So I'll spend the time that I have left to translate this to ordinary geometry. Can you remind me, like 10 minutes or 12 or 15?
Well, 15, you're a nice person, but
No, I will not take 20. I will not take 20. Okay, so now I will do basically the following. Sorry for going back. Yeah, so I will take basically these 2 slides and translate to the ordinary world. And, okay, so translations are in orange or yellow. Well, the first item is something we saw quite at the beginning. So pseudo-Euclidean vector bundles or metric vector bundles correspond to degree 2 symplectic manifolds. So spelled out, the structure of graded Lie algebra is the following. So remember the G tilde was a sum, had 3 components. One was called G, and then A and H. So one of these components, the one in degree 0, is the Lie algebra. There are 2 modules, and then there is one more funny map, maybe. And okay, the co-moment map, so morphism of graded Lie algebras. It also has three components, because G tilde has a component in degree 0, one in degree -1, one in degree -2. So we have 3 components that correspond to the 3 bullet points. And well, one is just a map, an ordinary map from the smooth manifold M, which is the body of curly M to the vector space H star. The other is a map that gives me a bunch of sections of E, of the pseudo-Euclidean vector bundle. And the third one is a Lie algebra map from the degree 0 part G into sections of the T algebroid, so covariant differential operators. And and I should definitely point out that the third bullet point, so the third bullet point gives you basically an action. Like for every element of the Lie algebra G, and honestly Lie algebra, I get an infinitesimal symmetry of my pseudo-Euclidean vector bundle. And so that gives, well, an infinitesimal symmetry. Yeah, I mean, that means that I have an infinitesimal action of G on E. And furthermore, restricting to the 0 section M, I get an infinitesimal action of the Lie algebra G on M. Okay, so let's translate further. Okay, 0 being a regular value, I didn't write it down. So the G action on M has to be almost free and a couple of more things. And so what about the 0 level set? Okay, so the moment map nu tilde is expressed in terms of the 3 components I had in the last slides. So the coisotropic will also be expressed in such terms. So for example, maybe look at the second bullet point. There's this isotropic subbundle K. It's just the image of this map that I had into sections of E. And okay, so yes, and the last 2 bullet points come from the action of the Lie algebra G on the pseudo-Euclidean vector bundle. From the third, forgive me for going back 1 second, from the third map phi there. So the role of the third map is to basically provide symmetries by which eventually we will divide. The role of the first map nu is to give you, as a 0 level set, a submanifold of M, and the map in the middle is used both to cut down this, to restrict to a submanifold and to divide out. It has a mixed roles. Okay, more or less obvious regularity conditions that one can assume. And then, applying like the previous work, you get a honest pseudo-Euclidean vector bundle, which takes this form here. So the quotients by the foliation and by, the leaf space of the flat connection, so to say, are the same thing as the quotients by the action of a connected, I should say, Lie group G that integrates the infinitesimal action on the vector bundle. So the bottom line is, in this Hamiltonian setting, when all the assumptions are satisfied, and I know there are many, you get a quotient space that is maybe a bit more explicit than this, because the various quotients you take are just, orbits of the G action. Okay. Yes, and then, so what about if we also have these degree 3 functions? So the fact that the moment map preserves the differentials too, translates into commutative diagram. I mean, okay, I should say which differentials to be precise. So now G tilde is a differential graded Lie algebra. So it means that I have a differential from the degree -2 component H to the degree -1 component A, and then from there to G. And some diagram, which was also present more or less actually in the work of Bursztyn-Cavalcanti-Gualtieri from 15 years ago. Such a diagram has to commute.
What's the thing on the bottom right corner all the way?
Yeah, so good question. So forget the CA for a moment. If you forget the CA, those are sections of the T algebroid, so infinitesimal symmetries. Infinitesimal symmetries of the vector bundle E that preserve the metric. So by writing CA, I mean I want infinitesimal symmetries of the Courant bracket too. That's what I mean. And okay, so these are basically the extra assumptions you have to put if you want the quotient to be a Courant algebroid and not just a metric vector bundle. Okay, so this gives some reduction procedure that I expressed here in classical terms. And so in our paper, actually, we have very few examples. I mean, we don't have concrete examples. We present classes of examples, mainly because in the previous literature, there were already many classes of examples. And I think the main contribution of our work is to recover everything in a systematic and unified way. But now I will specialize further to make things a bit more concrete and get toward examples that are present in the literature. So the special case I want to consider now is when the DGLA is, which is the thing up there, G tilde, is exact. So this by definition just means the following. Being a DGLA, G tilde has a differential, right? So the differential goes, so we have a map from H to A and then from A to G. Well, I want this to be a short exact sequence. Right, so an injective map into A and then a surjective map onto G. That's what I mean by exact DGLA. And so such an object can be, is in bijection with so-called exact Courant algebras. So the definition, so this is an object that arose like 15 years ago. So a Courant algebra is basically a map from a Leibniz algebra to a Lie algebra. So Leibniz algebra means that the Jacobi identity is satisfied but not skew symmetry. And you want it to be surjective and a couple of more things. So this simplifies a bit the picture because we have only two spaces there. I have A and G. So then I obtain a third space H by taking the kernel. To have two objects instead of three. And also, so having a differential graded Lie algebra morphism as moment map simplifies. This is a simplification with respect to the past two slides. Now, to have such a morphism, I just have to specify two components, not three. The third one comes for free. So a map from G to the T algebroid comes for free because the map from A to G is surjective. So I have two maps, satisfying the conditions you see there. And so in this, essentially was already contained in papers by Bursztyn-Cavalcanti-Gualtieri 15 years ago, at least in the case when E was an exact Courant algebroid, because they considered only that case. And so in this, this is like the framework they use to obtain some examples. Actually, there is a further simplification that I will address in a vague way now. So this is the last slide. So without getting into technical details, now Now I will basically present a way to obtain this data. So an exact DGLA and a DGLA morphism into a symplectic graded manifold, well, with Courant function. So I will be, well, conceptual rather than explicit. So, well, we need a Courant algebroid first. Let me take it of a simple form. So is the first line there, A plus A star, where A is a Lie algebroid. If you want, you can take A equal to the tangent bundle. So in this way, you recover the standard Courant algebroid. So the Courant bracket is the one that I had like in the first slide, the standard one, no twists, nothing fancy. And the corresponding degree 2 symplectic manifold is a graded cotangent bundle, T star 2 of A1. Okay, so my claim is that you get an exact DGLA and a DGLA morphism into functions on that very graded symplectic manifold, doing the graded analog of something that, well, we could tell our symplectic geometry students. And this is the way in which many, even though not all, examples in Bursztyn-Cavalcanti-Gualtieri, for example, arose 15 years ago. So before showing the last part of the page, well, let me show a simpler version of this, because, like, well, yeah, it's easier to understand. So, okay, I don't need to look. So in symplectic geometry, well, courses, we teach our students this. If we have a manifold, so N is just a manifold. If you have a manifold with a group action, then you can take the cotangent lift, right, on the cotangent bundle. So, well, as we know, the cotangent bundle is a symplectic manifold, right? It has a canonical symplectic form. And this has a moment map. This has a canonical moment map. And the corresponding, leave it like this. So what is this moment map? Well, I will describe the corresponding co-moment map. So a map from, I'm not sure how to write it, nu star maybe. So a map from G to functions on N, on T star N. Okay, I'm using my space really badly, sorry. So I'll write it here. So this is just the infinitesimal action. Because, so this here, actually the map takes values in linear fiber-wise linear functions, and fiber-wise linear functions on the dual of a vector space are just sections of that vector space. So the co-moment map is a map from the Lie algebra into vector fields on N. Well, that's just the infinitesimal action corresponding to the original action. So this is like from classical symplectic geometry. So my claim is that by doing the graded analog of a variation of this, we recover, well, many examples of DGLA morphisms and exact DGLAs. And the variation is the following. So I'm sorry that there are so many formulae, but let me tell you what the main point is. So it's basically this stuff here, but allowing not only fiber-wise linear functions on the cotangent bundle as well, components of the moment map, I also have some fiber-wise constant functions that are constant on the fibers. So in other words, they're functions on N. And furthermore, I don't just have G, I also take another, well, I take a Lie algebra module H, and then I take the semi-direct product. So what acts is like G cross H. So, okay, and here is where I stop.